Hi. Sorry we had to cancel class today, although it may have been the vacation that your body needed. But as you might guess, I'm not planning to write the class off, and so this video lecture is designed to finish our discussion of the fundamental theorem of calculus. I just have a few things to say about that, and then to begin talking about infinite series. You already have the notes through the fundamental theorem of calculus in hard copy. And the notes for section 8.1 for the series are posted on Learning Studio. If you care to, you can pause the video and print those out to follow along as you wish. For the fundamental theorem of calculus, let's talk about page 71, starting on page 71. So here's an integral formed in this sort of way where the variable is a limit of integration on the integral. And so by fundamental theorem of calculus, I'm supposed to find an antiderivative of 1 over t, which is of course ln t, to be evaluated at 1 and at x. So that's ln x minus ln 1, but ln 1 is 0, and so this is just ln x. All right, if you take a look at your calculus book, this is actually the most common way that the natural logarithm function is defined. Using a definite integral like this, this then becomes the definition of the natural log, and the properties then of natural log follow easily. For example, what is ln of 1? Well, it's just L of 1. It's just integral from 1 to 1 of 1 over t dt. And without even worrying about what happens regarding an antiderivative, I'm integrating from 1 to 1 of some function. I just get 0. Other things we know, when x is less than 1, then because the upper limit of integration would be less than the lower, ln of those numbers, like 0.5, are negative, whereas ln of numbers greater than 1 are positive, and so on. Lots and lots of useful properties of the logarithm come straight from this definition. The other problem I wanted to mention regarding the fundamental theorem of calculus is this one. Here's a function f defined so that the variable is an upper limit of integration. But this time it's not just an x up here, it's some function of x. The question is, what's the derivative of this function capital F? So let's tackle this problem by splitting this complicated function apart into some simpler pieces. Let's let u of x equal x squared because of what the upper limit is. And let's define a related function g of u to be equal to 0 to u sine of t squared dt. So obviously the pieces here that I'm picking aren't just random, they're related to the function in a very special way. So what is f of x in relationship to u and g? So my f, of course, has a x squared appearing right here. That is just u. So f is the compound function g of h of x. And so to take its derivative is a chain rule problem. So the chain rule says this is g prime of h of x times h prime of x, or g prime of u, if you wish, times h prime of x. And if I work out what these derivatives are, g prime is just to, like we did before, is sine of u squared. It's to take the upper limit of integration and plug it in as the variable of integration. And h prime of x is 2x. And the only thing remaining to do is to account for the fact that nobody wanted things in terms of u. I was the one that introduced that. So let's put x squared back in for u. So this is sine of and x squared, quantity squared, is x to the fourth. So that function, and then times the 2x. And you can play other games as shown in some examples in the text where various things are done to these limits of integration. And you can use this procedure to unravel it, take the derivative of the individual pieces, and then put the thing back together. And I'll skip the example at the bottom. So that is all that I wanted to say about the fundamental theorem of calculus. Now, let's talk about infinite series. This is Calc 2 material, obviously, so we'll recover some things from Calc 2 and extend them a bit. And in particular, this video is taken from section 8.1. So if we have a sequence of real numbers, AK, we can define what's called the sequence of partial sums by starting at the beginning, and for each sequence term, say the nth sequence term, I just add up the first n terms of the sequence AK. Let's look at an example. Here's a infinite series formed this way, and if I start forming the sequence of partial sums, S1 is just A1. Here the sequence AN is 1/2 to the n, or if I'm using the variable k, this is 1/2 to the first power. Whereas S2 is A1 plus A2, so that's 1/2 to the first plus 1/2 squared, and that's 3/4. And S3 is 1/2 to the first plus 1/2 squared plus 1/2 cubed, and that's 7/8, and I'll do one more. S4 equals 1/2 to the first plus 1/2 to the second plus 1/2 to the third plus 1/2 to the fourth. Turns out to be 15/16. And the question is, what happens to this sequence of partial sums? So if I form the sequence of partial sums 1/2, 3/4, 7/8, 15/16, what's going on with that? It's obviously increasing. It looks like it might converge. It looks like it might converge to 1. That's the question here. Does a sequence really converge? If it does, we'll say that this infinite series converges, or that the series is convergent. And if this sequence does not have a limit, then we'll say that the series diverges. This is the same converges, diverges question that you looked at in Calc 2. Let's do a few examples. Determine if the following series converge, and if so, find the sum. So here is the form for the first example, and let's look at what Sn, one of the terms, an arbitrary term in this sequence of partial sums, would look like. So the very first term is, notice that all of the terms will have a factor of 5, so I'll write those out in front. And then 1/3 to the k is the same thing as 1/3 to the k. So in the S sub n, the first term has a 1/3 to the first, then there's a 5 times 1/3 squared, 5 times 1/3 cubed, and plus a lot more terms probably, and the very last one, since I'm looking at the first n terms, the very last one is going to be 5 times 1/3 to the n. Now, I want to know what happens to this thing as n goes to infinity, but it's in a very awkward form. This plus ... doesn't let me see what's in there, and therefore I can't gauge whether this thing is growing or leveling off, or what S in the sequence is doing. There's a trick. This is actually a geometric series. Each term is 1/3 times the previous. And so if you actually multiply both sides of this equation by 1/3, then on the left I get 1/3 Sn. On the right, notice that each exponent is going to bump up by 1. I'm multiplying by 1/3, and so I'm going to shift things to line up like exponents. 1/3 times this is 5 times 1/3 squared, and 1/3 times this is 5 times 1/3 cubed, plus, and so it goes. The next to the last term is 5 times 1/3 to the n, and then the very last term comes from multiplying this by 1/3 and getting 5 times 1/3 to the n plus 1. The reason that's useful is that I can subtract. If this is equation 1 and equation 2, then subtracting equation 2 from equation 1, on the left-hand side, Sn minus 1/3 Sn leaves 2/3 Sn. And on the right-hand side, and the whole point of doing this is notice most of these terms cancel in pairs. Things that don't cancel are 5 times 1/3 to the first. This has no partner down here to cancel it. And then at the very end, there's another term that has no partner to cancel it. And so it's minus 5 times 1/3 to the n plus 1. I'm trying to solve for Sn, and so that almost does it. If we now multiply both sides by 3/2, Sn is 3/2 times 5/3 minus 5 times 1/3 to the n plus 1. Okay, and the question is still, as it always has been, what happens to this term as n goes to infinity? But now it's easy. The only n in the expression is here, and it's an exponent of a real number which is between 0 and 1. So as n goes to infinity, this term decays to 0. And what we get is, well, let's write it officially. Sum, k, equals 1 to infinity of 5 over 3 to the k converges to, and it converges by definition to the limit of this as n goes to infinity, which is 3/2 times 5/3, otherwise known as 5/2. All right. Next example that I want to consider is this one. So this is the famous series that goes 1/1 plus 1/2 plus 1/3 plus 1/4 plus and so on forever. You may recognize this one from Calc 2. It's called the harmonic series. And it's actually a bit challenging to decide whether this one converges or diverges. By that I mean you can plug things like this into a calculator and still not be completely convinced. Of course, the bigger the number of terms gets, the larger the sum gets, but it only grows very slowly. It turns out that the harmonic series is divergent, so we're going to show that this the sequence of partial sums does not converge, and the way we'll do that is to show that the sequence is not Cauchy. Remember, a sequence is convergent if and only if it's Cauchy. I'm trying to show the sequence is divergent, so we'll show that it is not Cauchy, and hence it'll be divergent. So Cauchy sequences, it's been a long time. What you have to do is pick two indices way far out and then discuss whether, say, if m is greater than n. So I have two indices, n and m, and then I discuss whether the s sub m term and the s sub n term are or are not close together. So let's look at S sub m minus S sub n. I'm assuming that m is the larger of the two. What's that look like? That's kind of a mess to write down. The S sub m part is going to be 1 plus a half plus a third and so on, plus dot dot dot. Eventually we're going to get out to a 1 over n term. Since m is bigger, eventually I get to n, and then the next one 1 over n plus 1, and then some more, and then finally I get out to the last term, 1 over m. Now for S sub n, I just get 1 plus a half plus dot 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 plus 1 over n. And notice that every single term that's in this sum is included in here. So this just cancels out part of this sum, and we end up with 1 over n plus 1 plus 1 over n plus 2 plus dot 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 plus 1 over m. I'm trying to show that this is not Cauchy, so I actually want to show that this expression is relatively large, or at least not small. So let's show that this is greater than something. And what I will do, so I want to show that this is larger than something. I want to show that each term is greater than something else. If we look at these and ask, what's the smallest term that we have here? Well, it's the one with the largest denominator. And the largest of these denominators is the last one, m. And so let's replace every term by a one that has a denominator m, plus dot 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 plus 1 over m. So for example, this term is greater than this one because it has a smaller denominator. This term is greater than this term because it has a smaller denominator, and of course the last terms are equal. So the advantage of doing that, of course, is these are like terms and they can be combined. I just have to know how many there are, and we are looking at going from term, well, you can see it here. We're counting up by 1, 2, 3, da 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 da, and we stop when we get to m minus n. So there are m minus n terms, each of size 1 over m. And so that's what this summation is. And if I rewrite this, this is 1 minus n over m. And the question is, does that have to be small? And the answer is no. If we take, for example, epsilon equal 1/4, we'll be able to show that this can be larger than epsilon. Then for any n, let's look at s sub 2n minus s sub m. Remember, m can be anything larger than n, so in particular m can be equal to 2n. And this one would be equal to 1 minus n over 2n, but that's a half, and that's greater than epsilon, which then shows that the sequence is not, the difference in terms of this sequence is not getting small, and therefore the sequence is not Cauchy, and therefore the series is divergent. Harmonic series diverges. Last example of this type is a series that looks like this. And you may remember things like comparison test and so on, and we'll get there in a moment. But let's try another trick on this one, and that is to use partial fractions. So this expression, 1 over 3k minus 2 times 3k plus 1. From Calc 2 and talking about partial fractions, we know that this is equal to two terms, the sum of two terms, whose denominators are 3k minus 2 and 3k plus 1. And if we just put an a for an unknown numerator here and a b for an unknown numerator here, then when we actually multiply this out, you can solve for constants a and b and find out that they both have to be 1/3. So I don't want to take the time to go through all of that algebra. It's not that important. If this sounds completely foreign to you, you might want to actually do this algebra. You get two equations and two unknowns, solve for a and b. The reason I want to do that is now let's rewrite the series, or in particular the nth partial sum. So if I just take from k equals 0 up to k equals n, then notice now that each of these individual terms is going to break into 2. So I'll have the terms now coming in pairs that are being added together, and each of them has a 1/3. So let's pull a 1/3 out of the whole thing, and then it's like 1 over this plus 1 over this. When k equals 0, which is where this series starts, then I have 1 over -2 plus, and I think I made a mistake. I'm sorry, yeah. Here is a negative. It turns out that b equals -1. So write it as plus here, but then you find out b equals -1/3, and so you can write it this way. Okay, so then when k equals 0, the second term is minus 1 over 1. Those get grouped together. Then the next pair is when k equals 1, and so we get a 1 over 1 minus 1 over, and when k equals 1, this term has a denominator 4, so there's a pair. Then there's a 1 over 4 minus 1 over 7, there's a pair, plus ... and then the very last term is when k equals n, and I get 1 over 3n minus 2 minus 1 over 3n plus 1. So close that pair, I'm out of room here, and then close the square bracket. All of that is times the 1/3. And now check out what happens inside here. Addition is associative, so I can take off the parentheses, and then what you see is a -1 and a +1 side by side, a -1/4, a +1/4 side by side, -1/7, +1/7, and so on. So in a different sort of way, these terms also cancel each other out, except for the very first term does not have a partner, and so that's -1/2. And this very last term also does not have a partner. That's 1 over 3n plus 1. By the way, this series is called a telescoping series, when you have this successive terms canceling each other and you just get the first terms and last terms surviving. Okay, and the question about convergence or divergence is what happens as n goes to infinity, but now it's an easy question. The first term is fixed, the second term goes to 0, and so the series converges to the limit as n goes to infinity s sub n. Just, you don't have to write this, but I'm pointing out what I'm doing here. And as far as what you get, it's 1/3 times -1/2 plus 0, or -1/6. The series converges, and here is the value of its sum. The next page of the notes is a table or a list of the convergence tests, most of which you've seen in Calc 2. At the moment, I'll just talk about the first two here, and then later on we'll come back and discuss the rest and do some examples. For now, I just want to point out the nth term test for divergence and Cauchy criteria. Nth term test says that a series whose nth term does not go to 0 has to diverge. So, for example, if I have a series like sum 1 over n over n plus 1, as n gets large, this term goes to 1, not to 0 in the limit, and therefore this thing diverges without any further discussion. But notice the converse is not true. So trick not to fall into is to say, well, since this term goes to 0, therefore the series must converge. No, it doesn't. We just showed that this diverges also. So this one diverges by nth term test. And this one diverges because of something else, but it's not by the nth term test. The nth term test is only a one-way sword. It shows divergence, but it cannot show convergence. The other test to point out here is the Cauchy criterion. And this is pointing out how fast, in some sense, the nth terms have to go to 0. So by the nth term test, we know that if the series is going to converge, then the sequence has to go to 0. So that means if I graph the terms of the sequence, here's n, here's a sub n. These things have to be decaying to 0. And the Cauchy criterion is saying, hey, somewhere we can hack off a number n. And now if I go out farther and pick up a bunch of terms, the terms between m and m plus n. So I'm picking up n terms, and I'm doing that arbitrarily far out in the sequence. The sum of those terms has to be small. In other words, this tail has to be dropping down to 0, and it has to be dropping down to 0 rapidly so that this is true for any positive epsilon. And we'll stop there. Thank you.